Okay, back to it. We are doing calculus, CLEP, calculus practice exams from PDFs I found online. They were here, link also in the description. Maybe they're still there, maybe they're not, who knows at this point. So where we left off, next is number 21 here. We are asking if your function is the arctangent of pi times x, then what is the derivative? And ooh, this is deep trigonometry stuff here. So let's briefly, what even is the arctangent? Well, if the tangent of an angle is some number n, then the arctangent of n is the original angle. It's just the inverse function. So what is the derivative of arctangent? I don't blame you at all if you don't want to memorize that. If you have the time, if you have the inclination to go off a cheat sheet and memorize all the wacky trig derivatives, be my guest. But if you don't, it's only gonna nick you on one or two questions on the CLEP exam, I think. So it's probably not super worth the time or the effort. But we'll work through this. Just for the record, the derivative of the arctangent, we'll say arctangent of x, is 1 over 1 minus x squared. Well, plus x squared, actually. Yes. So we're asking the derivative of arctangent pi x. So this becomes a chain rule application. So again, the chain rule, which you definitely do need to memorize, composite function f of g of x, the derivative of that equals the derivative of f as a function of g of x times the derivative of g of x. So in this case, our outside function is arctangent, and the derivative of that is going to be what we said, 1 over 1 plus x squared. The g, the inside function, is the pi times x, and the derivative of that, real easy one, power rule, x to the power 1 goes away, it is just pi. So we plug all those in. The derivative of f, and because it's the g of x as the function, so we're taking the g, which is the pi x, and filling it in to this x here. So it is 1 over 1 plus pi times x squared, and then multiplied by your pi there, the derivative of the g. And then what is the best way to simplify that? Right. So in the original question, it's actually not asking for the general derivative, is asking for the derivative of x equals 0. So this is our general form, but now we can fill in x equals 0, pi times 0 squared times pi. And because that's multiplied by 0, that just all goes away. 1 over 1 equals 1, and you're just left with pi on its own. So the answer here is E, which, again, you're only going to get if you happen to remember the derivative of the arctangent, which that's pretty tricky. You know, I personally have to look that up. I'm not going to remember that. So, but if you get a similar question, you know, it's good chain rule practice there, and just hope to not have so much trig be turning up on the real exam day. So let's move on to number 22. And we're saying we have a rectangle in the xy plane, just a rectangle on the graph, with its lower left vertex at the origin, meaning one corner is at 0, 0, and the upper right vertex, the other corner, is somewhere on this function, y equals the square root of 6 minus x. And what is the maximum area? What is the biggest that you can get out of this rectangle? So this corner is variable. It might be here, it might be here, it might be here. We don't know where that is. It's somewhere on this curve, and where on the curve makes the rectangle the biggest. So we ask ourselves, what is the area of the rectangle? Obviously, it's the base times the height. So the base is equal to x, and the height is, well, that's our function. It's square root of 6 minus x. So the area of the rectangle is x times 6 minus x. And now we have to decide for what value of x is that the biggest. So we're going to rewrite that again over here. The area equals x times the square root of 6 minus x. And that's a function. Again, we want to find where it's the biggest. We want to find the maximum of this function. And since this is calculus, the easiest way to do that is to take the derivative and then find where the derivative, the slope, is 0. And we're just going to presume incorrectly that is going to be the maximum, and that will tell us the x value, and from that we can figure out the area. So we need to take the derivative of that, and it's super messy. So we're going to do a little trick here to make it a little bit easier, and we're going to turn x into the square root of x squared times 6 minus x. And what that lets us do is multiply it in underneath, and then we can multiply those together. 6x squared minus x cubed. And again, just to be easier, we're gonna change that square root into an exponent of a half. Now, you know, why is the square root the same as an exponent of a half? Well, if you figure, you know that when you're adding exponents, if you have like x squared times x cubed, you're adding the exponents and you get x to the 5th. You know, if it was x squared times x squared, you add the exponents, you get x to the 4th. But what two things do you multiply to get plain x? What two exponents can you add? What two exponents that are the same can you add to get just plain x? And that has to be x to the half and x to the half. So we know that x to the half is the same as saying square root of x. It's just a different notation. Math does that a lot. Same way of two different ways of writing the same thing. But because we're going to do derivatives, a exponent of a half is just easier to work with for what we're going to do. And what we are going to do is the chain rule. So again, for the chain rule, you have the composite function f of g of x, and the derivative of the f is equal to the derivative of f by itself times the derivative of g, well, the derivative, that's probably not the proper notation. But anyway, this is the formula for the chain rule. So our f is going to be the outside function, which is going to be x to the half, the x representing everything that's in there, which is our g 6x squared minus x to the third, because all of this is inside of that for our original function. So then the derivative of the f, bring the exponent down 1/2 and subtract 1. So it's going to be x to the minus half. And that's an odd thing. I know it's an odd thing, but it's what it is. And then the derivative of the g, again, simple power rules, bring the 2 down. 2 times 6 is 12. Subtract 1, that's just x to the power 1. Minus, bring the 3 down. 3 minus 1 is x squared. So now we can take that and fill it all back in. So you take the derivative of the x, you have the 1/2, and then the x gets filled in with the original g of x, which is this. So it is 6x squared minus x cubed to the power of -1/2, multiplied by the derivative of the g, which is here, 12x minus 3x squared. Well, that's still kind of messy, isn't it? So first we have to deal with the negative exponent, and what does a negative exponent mean? Basically, it means the inverse. And why is that? Well, if we say, for instance, if we take x to the 5th divided by x squared, that simplifies down to x cubed, because 5 minus 2, you're dividing. 5 minus 2 equals 3. But what if we also did x to the 5th times x to the -2? Well, that's the same thing. If you add 5 and -2, you get x to the 3rd. So from that, we established that 1 over x squared is the same as saying x to the -2 power, and so on for any negative. It just makes the whole thing inverse. So we take this thing, we stick it under the fraction bar, and it gives us 1/2 times 6x squared minus x cubed to the 1/2 power, and then that's multiplied, so it goes up on top, 12x minus 3x cubed. And that's still pretty messy. So you ask, well, what can we do more from there? What can we pull out of these things? So up on top, we can pull out a 3 and we can pull out an x. So we got a 3x, that leaves a 4 here, and that leaves a minus x there, because if you multiply that, you get that. And on the bottom, we can pull out an x squared, but we have the half power, or the square root, so when we pull the x squared out of it, it just becomes plain old x again. And then we left inside 6 minus x to the half power. And he goes, and again, it would be, if I did it in 2 steps, it would be x squared to the half power times 6 minus x to the half power. And then we just simplify that out to a plain old x. So it's still a lot. What can we do with this even more? Well, the x's cancel out. So we can say 3 halves, 4 minus x over 6 minus x to the half power. And that's about as good as we're going to get it. But let's remember what we were looking for. This is the derivative of that area function. We want to find where that derivative is equal to 0, because we're presuming that's going to be the maximum of the function. So what can we do with this to make it turn out to be 0? And the quickest thing that we can think of is if we can make the top of this fraction be a 0 by putting x equals to 4. The 4 goes in there, that's 0. It doesn't matter what's on the bottom, it just all goes to 0. So we're going to stick with x equals 4, and we're going to put that into our original area function. 4 times 6 minus 4. X, 4 goes there, 4 goes there. We're left with this. That simplifies down to 4 square roots of 2. And in fact, that is one of the options here, 4 square roots of 2. That's the answer D. Okay, moving on. Number 23. Let f of x, the function, equal x cubed plus x. If h is the inverse function, then the derivative of h at the x value of 2 equals what? Okay, tricky words here. What is the inverse function? In context here, when we say inverse function, we're just talking about flipping the x's and the y's. So you're kind of taking the graph and flipping it over that way, switching the x's and the y's. But the trick here is it is only asking for the derivative of that resulting function at a particular point. So we don't need to figure out what the inverse function is. We just need to know, well, we want to know the slope of the inverse. Let's rewrite it over here. F of x equals x cubed plus x. And we want to know the slope of the inverse, where x equals 2 for that inverse function. That means in the original function, there's going to be the slope, or the slope flipped over, where y equals 2 for the original function. This is going to be just the inverse of this, the reciprocal of this, of 1 over the slope, for 1 over the slope of the original function at y equals 2. That's it's one of those things where you got to kind of decode what they're asking for. But yes, if you have a graph and you flip x and y over, the slopes, it's the same slopes, just x and y flipped, which means you're flipping the slope upside down, because the regular slope is, delta y over delta x, and if you reverse those, it's delta x over delta y, so it's just 1 over the slope of the original formula. So we're asking ourselves, for what x value, we need to figure out the x value. Where is that going to equal that? And not a lot to solve here, just by examination. What's the only thing that's likely to be? It's got to be x equals 1. 1 plus 1 is 2. So what is the reciprocal of the slope of the function where x equals 1? So we need to find the slope at x equals 1. We do that with the derivative. So this is just a simple power rule. Bring the 3 down. 3 minus 1 is 2. And then plus x to the power of the 1. Bring the 1 down. The x goes away. So the slope for the value of x equals 1, here's 1 squared plus 1, turns into 3 plus 1, turns into 4. So then what is 1 over that slope is going to be 1 over 4. And if we go back to our original problem there, we see that 1 over 4 is one of the options, so that is our answer. Choice B there. So done with that. Let's move on to number 24. Let f be the number of trees in the forest at time t in years if f is decreasing at a rate given by the equation df over dt equals negative 2f, and if f of 0, meaning 0 being the time, meaning you're starting at 5,000 trees and losing, negative 2 times f. This is an exponential decay question, which is the opposite of exponential growth. Exponential growth being something like interest in a bank account, or population growth if you have a certain number of bunnies and the bunnies reproduce at a certain rate. How many bunnies are you going to have after a certain number of years? That type of thing. But if the growth is negative, then it's exponential decay. And you can derive that from that with a lot of effort, but the more general, familiar form of the exponential growth takes the appearance of p for population equals p0, meaning the starting population, at 0 time, 0 for 0 time, times a being the rate of growth or rate of decay to the power of t. And we're going to use some other logical tricks to figure out which of these fits that, rather than starting from that and doing the derivation, because the derivation is a little messy, not something we want to deal with. So first of all, we know that we're getting a decreasing rate, and if you look at D and E here, it's adding to it. So we know that whatever answer we have is not going to be something more than 5,000 where we started. It's got to be something less than that. So it's not going to be D, and it's not going to be E. And if we look at C, this is decreasing, but that is a linear decay. Loses, and what this is saying is it loses 2 trees a year, when the actual rate of decrease is related to the size. You lose every year. You're losing 2 times what the population is in the forest, meaning, the bigger the forest, the more trees you're losing. That makes a little more sense if we were doing growth. If you're doing a population growth, the bunnies, the more bunnies you have, the more baby bunnies there's going to be. That's why it's exponential growth. The more you have, the faster it grows. So this is the same thing in reverse. The more you have, the more it decreases. It's a math problem. What can you say? But that is a linear decay, going down by the same rate for every t, not an exponential decay. So we know that's not going to be it. It's not linear. It is an exponential decay. So it's not going to be that. So between A and B, and these are the ones that most look like that one. But we can figure that look at this one, because you have the T is down here, and we know that at T equals 0, the whole thing is 5,000. So when you plug in 0 for T, you should get the 5,000. If you plug in 0 for T here, it's going to equal 0. So that doesn't work. So that's not it. Whereas, here, if you plug in the 0 for the T, you end up with e to the power of 0, which is just 1. 1 times 5,000, so that fits. At t of 0, the whole thing is 5,000. So that's what we're left with. We can deduce it logically without doing any real math, and that is the answer. And if you just be vaguely familiar with that form, but again, this is the kind of thing that is not dwelt on for very long within a calculus course. So, probably maximum 1 question like that. 2 at the most, but probably just 1 for that kind of question on the exam that you'll get, I would think. Okay, so 25. Let f be the function defined as the square root of x, using the line tangent to the graph. Tangent meaning it has the same slope at that point. So we're at x equals 9, so we know we're going to be finding the derivative of that at x equals 9 to find the slope. And what is the approximation of f of 9.3, i.e. the square root of 9.3? And this approximation stuff, basically we're saying there's a square root function, and you'll note it's a sideways hyperbola. It's kind of an inverse. Normally when you have y equals x squared, it's a parabola going up this way. But if we flop the x and the y, then you get a sideways hyperbola, and you only take the top half, because it still has to be a function. But the trick here is that you're taking the tangent line at x equals 9, and then we want to approximate the value at 9.3, and you have this tangent line that's going to be a little bit above the y equals the square root of x, but it's still going to be pretty close to there. This is the kind of approximation, if you don't have a calculator and you want to be able to figure that out quickly, this is the kind of approximation that you might do to get pretty close to 9.3, because it's easy to calculate this at the 9, easy to figure out the slope, and that's going to be pretty close. So let's get to it. So we need that slope, we need the derivative of x squared, square root of x rather, and again we're going to convert that square root to x to the power of a half, and take the derivative power rule, bring the half down. 1 half minus 1 is x to the negative half power, and then just for convenience, we're going to rewrite that in the more traditional manner. So we start by taking the reciprocal 1 over x to the half, and then we can even go as far as to say 1 over the square root of x, or if you prefer, just 1 over 2 square roots of x. So we want to know all this where x equals 9. So we can go ahead and fill that in. It's not 3 yet. Square root of 9, that becomes 3. That becomes 1/6. So that slope, the slope of that tangent line, is 1/6. And we also, at this point, we need to know the y value, the point on that graph at 9. Well, if y equals the square root of x equals 9, so the y value is 3. And we need to know that because we need to know the formula of that line in the traditional y equals mx plus b formula for a straight line, where m is the slope and b is the the y-axis intercept, how high or low it is. So we know most of these things. If y equals 3, the slope is 1/6, the x value is 9. We need to figure out that value for b. So we can simplify these things. 9 over 6 is the same as 3/2. And then we bring that over to the other side. 3 minus 3/2 is going to equal that b. And 3 minus 3/2 is still just 3/2 actually. So now we know the full formula for that tangent line. Y equals 1/6 x plus 3/2. And we're supposed to be finding what that y is going to be for the x of 9.3. So 1/6 times 9.3 plus 3/2. And again, this is one of those, we're not to the point where we're allowed to use a calculator yet. So in your head or on paper, we'll just do some regular long division. 6 goes into 9 one time, left with 3.3. 6 goes into 3.3 0.5 times, gives us 3.0, leaves us with 3. We get another 5. So y equals 1.55 plus 3 halves is 1.5 if we want the decimal. And we can add that together, 1.5 and 1.5 plus an extra 0.5, 3.05. So, and this is one of the rare ones where it is not a multiple choice. They expect you to fill in the box. And that is 3.05. Simple enough to do without a calculator. Would have been nice, but you can still manage. And that's it for now.